Let's take a look at section 16.8, which is going to cover Stokes Theorem. So just a couple of learning objectives this time. Defining the orientation of a curve, step one, and then we'll state and use Stokes Theorem. So starting with the orientation of a curve, we're going to start with defining a redefinition of a simple closed curve, which is any curve that starts and ends at the same points and does not intersect itself. Two examples of simple closed curves are drawn to the right, along with the two new orientations that we're going to want to have. So a simple closed curve will have a positive orientation if its parameterization traverses the curve exactly once in a counterclockwise direction. So both of those two pieces are important there. So the exactly once part and the counterclockwise part are both important for the positive orientation. And so the negative orientation will be the same setup, but it'll do the reverse. It'll still traverse exactly once, but the clockwise direction is going to be negative. So over to the right, drawn out both a positive and a negative orientation. So positive again is counterclockwise, while negative is regular clockwise. Ooh, no, that was supposed to be green. Counterclockwise. All right, so then Stokes theorem, which is just going to be Green's theorem, but brought up to 3 dimensions instead of just 2. We'll assume that S is an oriented, piecewise smooth surface. It's bounded by a simple closed curve with a positive orientation, the important part. And F will be the vector field whose components have continuous partial derivatives in an open region in R3, and that particular space contains S. Then we can relate the line integral of f dot dr to the surface integral of the curl of f dot n dA. And here n is going to be the upward pointing unit vector or some other positive oriented unit vector. So we talked about orientations of surfaces a couple sections ago, and we defined both upward and outward. So we might need to use either one of those two. But again, we'll want whichever orientation we create to be positive, we'll want to make sure that our normal vector n points in that positive direction. So if it's an upward direction, that just means that the z component is positive, or possibly some other orientation that we'll probably see an example later on. So as long as we have a parameterization of our surface, and that parameterization is r, then our unit normal vector n can be the two partial derivative unit vectors, ru and rv. Take the cross product of those and then divide by the magnitude of that cross product. And that's how we'll get to n. All right, and then a slightly different way to write Stokes theorem. So we'll start by defining the closed line integral, which is what that small circle in the middle of the integral symbol means, is that we're integrating over some closed curve, or a line integral over some closed curve. And that's a notation that's particularly common in physics. We won't use it too much in our course, but it's something that you'll probably want to be aware of. It's just if C is a positively oriented and closed curve, then we can write that there's the line integral with the closed circle, meaning that it's a line integral over a closed curve, is just the same as the line integral of f dot dr. We'll also define the boundary of a region D as delta D, just to give us an extra bit of notation, so that in the rewrite of Stokes theorem, we'll use that closed integral sign and delta s instead of c to represent that we're taking that line integral over the boundary of our surface S. And so again, the big thing that Stokes theorem does for us is that it relates a line integral over the boundary of a surface to the surface integral of that same surface. So a single line integral versus some sort of double surface integral. We can relate the two together with Stokes theorem. So let's take a look at some examples. So in this first one, we're going to compute the surface integral of the curl of f dot n ds, where f is some vector field. S is going to be the part of the sphere of radius 2 that's centered at the origin, and it lies inside the cylinder of radius 1 and extends in the z direction. And we want it to be above the xy plane, since there really would be two intersections that we're talking about here. We have one that's on the top of the circle and one that's on the top of the sphere and one that's on the bottom of the sphere. Since we're above the xy plane, we'll be looking at the one on top. So above the xy plane will be important for that positive that we're going to take here in a minute. So if we look over to the left, we have a figure 4 from the text that shows this particular surface that we're after. So that surface S is shaded in blue, and the boundary of that surface is going to be C. So C and delta S would be the same thing here. And keep in mind that delta S and ds are two separate things. Delta S is going to be the boundary of our surface S, whereas ds would be just the integrating factor, like dA or dx or whichever integrating factor we need. In this case, ds, because it'll be along the surface S. So since we're going to be using Stokes theorem, and we're attempting to calculate the surface integral, the steps that we're actually going to take will be to set up the line integral version. So we're going to change this surface integral into a line integral and then go from there, which means that we need to parameterize the boundary of S. So step 1 is to figure out what that boundary looks like. I have two equations, one for a sphere, one for a cylinder, and if I want the boundary, that means I want the intersection of those two curves, those two surfaces. So if we set those two equal to each other, I know that x squared plus y squared is 1, which means I get the equation 1 plus z squared equals 4. So just taking that intersection, which means that z must be equal to the positive square root of 3. So subtract 1, take square root of both sides, we get plus or minus square root of 3. But again, we're going to want to take the positive square root of 3 because we wanted the part that was above the xy plane. So now that we have our two boundary equations, one of those is the cylinder, x squared plus y squared equals 1. The other is just the equation z equals the square root of 3. We can parameterize those two pieces to come up with r of t. We're going around a circle, so we're going to use cosine and sine for x and y. And z we found was the square root of 3, so we'll parameterize z with just the square root of 3. We're also going to need r prime. So we'll take the derivative of that boundary curve and get negative sine t for the I position, cosine t for the j position, k0 for the k position. All right, that's all the setup that we're going to need. So now we should move on to the actual calculus part of the integral. So just doing all these integrals out. So we said by Stokes theorem, we can relate a surface integral to a line integral. So that's exactly what we'll do. So we end up needing just the standard integral of our vector field with the boundary plugged in, or the parameterization of the boundary plugged in, dotted with the derivative of that boundary vector. And since we're going to go all the way around the boundary, and the boundary is one circle, we're going to integrate from 0 to 2 pi for t. So if we take that dot product, we'll get the result that's shown below. F was the field xz, yz, xy. So just substituted those pieces in. You can see that colored in purple, yellow, and magenta. The result of that dot product ends up being two terms that are identical, except one is positive and the other is negative. So those pieces add up to 0, meaning we're just going to integrate 0 from 0 to 2 pi, which will just come out to 0. So one interesting point that we should probably talk about right here is that when we're taking the surface integral, or the surface integral of the curl of f dotted with its normal vector, we find that the only part that's important for calculating that surface integral is its boundary, which means I could have two different surfaces with the same boundary, and that surface integral of the curl is going to come out to the same value both times. It's one of the results that we get from Stokes' theorem, which means that if we're attempting to calculate the surface integral of some surface, or the surface integral of the curl of some field, and it's a particularly difficult surface integral to calculate, we could replace that surface integral with another similar looking surface integral, but one that has a different surface with the same boundary, which we might find a little bit later on. You may find there's a problem where you're asked to calculate the flux heading out of five sides of a box, like some sort of square box. And rather than calculating that surface integral over five different sides, we could just calculate the surface integral over the one missing side. And because those two surfaces have the same boundary, we know that it should be equal. So something worth noting. And then let's take a look at another example. This time we'll do the reverse. We're going to evaluate the line integral of f dot dr, where c is the positive oriented boundary of the square given by 0, y, z, where y is between 0 and 1 and z is between 0 and 1. And we're going to take the field y, z, x. So since we're still using Stokes' theorem and it's asking us to calculate a line integral, we're going to use Stokes' theorem to set up a surface integral instead, which means that we're going to want to parameterize the surface rather than the boundary. So the boundary is the piece that's drawn in green, and it's positively oriented, so we know that it should go counterclockwise. And since we know that this thing is in the YZ plane, its normal vector should point in the x direction. And if we use the right hand rule to trace this thing counterclockwise, curl your fingers around in a counterclockwise direction and your thumb should point in the positive z direction. I'm awful at drawing hands, so if you are curious about the right hand rule, or if you're unfamiliar with the right hand rule, I'm sure you could just Google it and come up with a better description that I could provide here. But we know that from the right hand rule that our normal vector should point in the positive x direction. Further, it should be a unit normal vector, and everything is in the YZ plane, so that normal vector is always going to be 1, 0, 0. So that's one approach that we can take to finding that normal vector. I've also parameterized the surface and then found the normal vector that way. So we're just going to use u for y, v for z, take partial derivatives of each. So then the cross product of those two partial derivative vectors is just the vector 1, 0, 0. We'll also need the magnitude of that cross product, which is just 1 in this case. But then to calculate the unit normal vector, take the cross product, divide it by the magnitude, and we come up with 1, 0, 0. Since we're doing the surface integral part of Stokes' theorem, we're also going to need the curl of f. So I've calculated that here as well. Finally, to just do the math, we want the line integral of f dot dr over the boundary curve, which is c, the part that was in green, and we're going to relate that to the surface integral over the surface, which is s, that's in blue, of the curl of f ds. So we'll just bring all that stuff in. Also, it looks like we're missing a part here because that should be the curl dotted with n, which is that unit normal vector, which we spent that time calculating. The curl of f is just -1, -1, -1. That unit normal vector is 1, 0, 0. And u and v both go between 0 and 1, because that's what y and z both did. So we do that double integral, or those iterated integrals, on -1, both going from 0 to 1, and we should just come up with -1 as our result.